As we have discussed in the last class, this was the Planck's radiation law, which actually described the experimental graph of energy distribution from any surface which is at a particular temperature T. We also have shown in the last class that Wein's distribution law was able to explain the experimental graph for very high frequency range. Rayleigh-Jean's law, which was able to explain the experimental graph in the lower frequency range. And we have seen that as the frequency increases, the Rayleigh-Jean's law was away from the actual experimental graph. This phenomena is called ultraviolet catastrophe. So, why it is called ultraviolet catastrophe? Catastrophe means disaster. And as it is in the higher frequency range, that means in the ultraviolet region, so this is called ultraviolet catastrophe. Actually, this ultraviolet catastrophe concept actually led to the formation of this Maxwell's Planck's radiation law. Okay. Now we will see that as Planck's radiation law was able to actually explain the experimental graph. So in the Planck's radiation law, if we put lower value of frequency, it should be able to explain, it should be able to come to the expression of Rayleigh-Jean's law. If in that expression we put higher value of frequency, it should able to derive the expression of Wein's distribution law. I have already done the calculation here. You see, when frequency is less, that means if nu is less. If nu is less, then obviously h nu by kt is also very less than 1. If h nu by kt is also very less than 1, we can rewrite this energy density function as u nu d nu is equal to 8 pi h nu cube by c cube. E to the power h nu by kt is very less than 1. So I can write it as 1 plus h nu by kt plus the other terms, then minus 1. So obviously this 1 will cancel out, and if we rearrange this, we will get this expression. And in the last class I have shown that it was the result of expression of Rayleigh-Jean's law. So in the lower frequency region, from the Planck's radiation law, we derive the Rayleigh-Jean's law. Now see, if we take the frequency in the higher range, that means nu is high. If nu is high, h nu by kt is also very greater than 1. If h nu by kt is very greater than 1, we can neglect this 1 with respect to e to the power h nu by kt. C to the power h nu by kt. By rearranging this, we get this equation, and we have shown that this is the Wein's distribution law. Okay. Now we will explain with the help of this Planck's radiation law how we will get Wein's displacement law and Stephen's law. Okay. This is the Planck's radiation law. Now we will derive Stephen's law from Planck's radiation law. What this Planck's radiation law says? It says the amount of energy emitted by the body within the frequency range nu to nu plus d nu. And you remember in Stephen's law, we have said what this law states. It states that amount of energy emitted from the body per unit time per unit area. So if we integrate or if we take sum of this Planck's radiation law from the range 0 to infinity, it will give the total amount of energy, because it is the energy density in this only particular frequency range. So if we want to find the total energy coming from this body, we have to take the summation of nu for all values. That means we have to integrate this nu value from 0 to infinity. Then it is very simple. So 0 to infinity u nu d nu, put the value of u nu d nu, then you take the integration. I have taken this h nu by kt as eta. I have just define it. So nu will be eta kt by h, therefore d nu is equal to kt by h into d eta. Then I have substituted the value of nu, that is eta kt by h, and then d nu, that is kt by h into d eta. Then the constant terms, I have taken it out from the integration. So we will get this integration. It is a very standard integration whose value is pi to the power 4 by 15. That is not very important. Important thing is that, see, here we already get in the derivation as t to the power 4. That means total amount of energy emitted from the surface per unit time per unit area is proportional to t to the power 4, which is actually the Stephen's law. Now we will derive the Wein's displacement law from this Planck's radiation law. Okay. So this is our Planck's radiation distribution law in terms of nu, that is energy density in the frequency range nu to nu plus d nu. Similarly, if we convert this equation, now I am going to derive the Wien's displacement law, which is lambda m into T is equal to constant. This constant value is 0.289 centimeter Kelvin. So if we plot u lambda d lambda versus lambda, this is the graph. Now if we want to convert this u nu d nu in terms of u lambda d lambda, simply there is no big calculation, it is just nu is equal to c by lambda. From here we can find d nu, and by substituting all the values we will get this u lambda d lambda value. That means energy density in the now the wavelength range lambda to lambda plus d lambda is given by this equation. Now Planck's radiation, Wien's distribution displacement law is that the energy density is maximum at a particular value. If we are going to find the maximum or minimum value of any function, what we do? We find its derivative, and at that particular value, that derivative is equal to 0. We will apply that theory. We will find du d lambda at lambda is equal to lambda m. That function is equal to 0. We will find the derivative of this quantity. This is the derivative of this function with respect to lambda. Then I have just simplified, and after that we arrive at this equation, and here I have taken hc by lambda m kt as x. So it is x e to the power x by e to the power x minus 1 minus 5 is equal to 0. By solving this equation you will get x equal to 4.96, which is nearly equal to 5. So put the value of x, that is hc by lambda m kt is equal to 5. So lambda m into t is equal to hc by 5k. H we know the Planck's constant, that is 6.626 10 to the power minus 34 joule second. We know the value of c, that is speed of light 3 into 10 to the power 8 meter per second. We know the value of Bohr's constant. All these values after putting we will get 0.289, which is actually the Wien's displacement law. In this way we have derived all the laws, that is Rayleigh's law, then Wien's distribution law, Wien's displacement law, then Stephen's law we have derived from Planck's radiation law. And it also explains the experimental graph. Thank you.